Okay, so let's start today by getting through kind of some definitions. This is going to be your first experience in heat transfer with like the differential equations. So let's go through the process and kind of lay everything out step by step, get to what we need to understand how to do this. Okay, so a couple definitions to start. It's a little small. So a couple definitions. These are my definitions. These are kind of loose, not formal. But first we'll think about a domain. Okay, so we're thinking about a conduction problem, which is some solid, and we're looking at how heat transfers through that solid, and what the temperature profile is. So we want to come up with an equation, some representation or a model of what's happening in that conduction. So we need a domain, right? We need a place where the function that we're going to derive is valid. So that's basically the definition I've come up with there. To get to that, to get to the function, we need to do a control volume analysis. So we're going to define a control volume. The control volume is what we call the subject of our analysis. We're doing the energy balance in this. Subject of our analysis in which the laws of conservation. Okay. So Mike keeps cutting out. Sorry about that. Okay, so the laws of conservation. So let's kind of graph this out a little bit. So if we're talking about a domain, let's start by kind of drawing, this is our conduction problem, this rectangle. So this is some solid body, and we're conducting heat across this solid body. So here I'm going to define a domain. It's a 1D problem, let's say. So I'm going to say this has some coordinate x associated with it. Right? The x is our dimension that we're going to be modeling. So x is in this direction drawn by the arrow. With a domain, we also have to define like the values that correspond to the limits of that domain. So in this case, let's say this is going from x equals 0 out to x equals L. Right? It doesn't have to be 0. Or you could set your coordinate system up where it's outside the domain. But here, it's easy for us in this situation just to say x equals 0 to x equals L. Right, so that's our mathematical domain. A control volume is different, right? If I were to draw a control volume for a conduction problem, how would I draw it? So stop and kind of think for a second. If I have to draw a control volume on this, how am I going to draw it? So there's a bunch of ways you could think to maybe do that. Turns out we're going to draw it like this. So I have one coordinate, x, that I care about. I'm going to draw a control volume. This is like infinitely small slice. And so the width of this control volume here is dx, right? Differentially small slice in the direction that I want to model. Right? So that's really important. We have a 1D problem. We're only looking at heat flow in the x coordinate. And we'll get to kind of why we can make that assumption in a second. But we have 1D in x. We draw a differential element in that direction. And that's our control volume. So now I'm going to be doing control volume analysis on everything kind of inside this, everything inside this domain here, right? That's my control volume. All right, so let's write out the equation for Fourier's law again and just kind of see how that relates to this problem. So in the most general sense, we said q dot double prime is equal to minus k times the gradient of temperature. So for this problem, our domain is in x, right? It's in one dimension. So if we applied this, the most general form for Cartesian coordinates, right, so for Cartesian coordinates, it would look like this. Q dot double prime equals minus k times the sum partial t with respect to x plus partial t with respect to y plus partial t with respect to z. Okay, so for this problem in one dimension, everything not in x goes away. Right? There is no temperature gradient in y. There's no temperature gradient in z. Right? By the way, I'm talking about here, this coordinate here would be y. And then if you had this sort of three-dimensional shape, this coordinate here would be z. Okay, so we're only talking about x. Everything else goes away, so here we'll say q dot double prime in the x direction is equal to minus k, I guess, partial t with respect to x. But because only x is involved, is the only independent variable, it's actually just minus k dt dx. Right, so we kind of started with that equation. We end up back at that equation just by going through the general steps and then saying, all right, this is not a PDE, it's not a partial differential equation. It's an ordinary one because we only have x, a single coordinate involved. Right? So this is the ODE, ordinary differential equation. This is the partial differential equation. So you can imagine as you go through, like in more complicated scenarios, maybe you have temperature gradients in x and y, you're going to start seeing two coordinates show up. Then you have to introduce PDE solution methods, and that becomes kind of difficult, right? So for now, we're going to just focus on the one dimension, get through that, understand that. All right, so let's maybe take an example here of heat transfer in one dimension. So what I've drawn is this, what we call a plane wall in one dimension. So what you're looking at is, it's this three-dimensional geometry. Just kind of finish this off here. All right, so this three-dimensional geometry, but I want to kind of talk about what this plane wall idea is. This nomenclature is a little bit weird. What is a plane wall? So a plane wall is basically a wall that has some finite thickness, but it's big enough in the dimensions other than that thickness that you can neglect any variation. Right? It's basically infinite. So we're saying, you've got these arrows up here, so this is infinite in this direction, infinite here, infinite here, infinite here, right? And you have some thickness, let's call this down here L sub x. That is the thickness of the domain. So why would we want to model things this way? Well, if you take, say, a large enough surface, then you can neglect the end effects. Normally, you'd say there's something going on that very top surface, like right up here, maybe this is insulated or it's exposed to heat flux or something like that, right? There's something different happening on the edge. If it's a big enough system, then you can just kind of look in the middle and ignore the end effects. So often we'll take this approach of looking at a plane wall as our starting point for 1D analysis in Cartesian coordinates. All right, so let's take this, this idea and go a little bit further with it. So let's say in this example we have some heat flux, and I'm applying a heat flux uniformly to this surface on the left. Right, that heat flux is of magnitude q dot double prime, right? So it has some units watts per meter squared. And the question is, in this situation, I've got a uniform heat flux. The plane is essentially infinite, but it has some thickness. Will there be any temperature gradients? Will there be any reason for heat to flow in any direction other than x? Right, think about that for a second. Uniform heat flux, infinite in all coordinates but x. Will heat flow in y or z? Right, the answer is no. There's nothing that causes that to happen. There's no temperature gradient that's going to cause heat to flow in any direction other than in x. So for this type of situation, we basically say, all right, I've got some temperature over here. Let's call that TH. I've got some temperature over here. Let's call that TC. TH and TC are only a function of, are only related to the heat flow in x. They do not depend in any way on y and z. All right? So in this situation, we would maybe write things out like this. We'd say q dot is equal to q dot double prime times AC, right, this cross-sectional area. So we're kind of starting to treat this as a 1D model. Q dot double prime is our flux. AC is this area that I've noted in green. Okay, so AC. So one thing that you often will get tripped up on, as you're going through this, you kind of get confused about what area am I using. So for almost all cases, or for any case where you're looking at conduction in a particular direction, this cross-sectional area is the area that's available for heat flow. All right, so here we're talking about heat flow in X. So the area is the Y and the Z part. It's the Y and the Z plane. In this case, it's infinite, right? So for this, we would just do maybe a per unit area type analysis. But anyways, if you have a finite area, you just plug that in there. And that's how you get the total heat flow. All right, let's see. I want to write out Fourier's law one more time just to kind of make one point before we go to the next slide. So Q dot is equal to minus K. Now it's not Q dot double prime anymore, right? It's just Q dot. So we have to multiply by the area, AC, times dt dx. So in this case, AC is constant, right? AC, this area that's available for conduction, is not changing as a function of x. So if that's the case, then when we're going through the ODE solution, this stuff here, it's all constant. But I want to make the point that it doesn't have to be, right? You can have a geometry, like well, if you look at the homework problem, right? The geometry in the homework problem does not have a constant cross-sectional area. So when you're going through the solution, you have to kind of keep that in mind, right? It makes it a little bit more complicated. You got to deal with it. I just want to make that point. All right, the last point I'll make before going to the next slide is this word adiabatic here. Okay, so adiabatic is a word you're going to become familiar with. It means that there is no heat flow across a particular boundary. So in this example, we could equivalently model this entire system. So if I were to just kind of draw this in 2D, like this. So we have our heat flux coming in over here, Q dot double prime. This is our X coordinate. This is our Y coordinate. I could model this entire infinite plane by saying, I'm going to perfectly insulate the top here. By insulation, I'm drawing these little hatch marks, and also on the bottom. So if I do this, that perfect insulation prevents any heat flow from going up or from going down. So it acts effectively like an infinite surface, right? There's no reason for heat to flow across that boundary. So that is what we call an adiabatic boundary. So this is adiabatic boundaries here, all right? Just keep in mind, adiabatic means there's a particular plane through which heat does not flow, okay?